So first, I'd like to say thank you for the opportunity to speak at this Foxconn event. For me, it's super exciting to see new companies coming into quantum computing, and especially a company like Foxconn that has such a great engineering tradition, because that's exactly what quantum computing needs right now. And I'm going to talk to that in this talk. So I got obsessed by quantum computing 2 decades ago. I was an undergraduate, and for me, the idea that we would use quantum mechanics to do computation was really pretty wild. The strange properties of quantum mechanics, like superposition, are used to our advantage in a computation. This is such an amazing idea, and the past 2 decades has seen huge progress in our ability to realize that potential. So today I'm going to talk about 2 things. The first is why quantum computing is such an exciting topic, has a huge potential. And the second is the challenges that we need to solve in order to realize that potential. So I'm going to start by taking a step back and thinking about computation. Computing is central to the design of many new products, from the layout of an electronic circuit to the design of a new aircraft wing. We use simulation and computers in order to design the next generation system, the next generation product. So to dig into that a bit more, the aerospace industry, for example, is really built on simulation. In the turn of the last century, the Wright brothers discovered flight. They discovered planes through trial and error. They built models and they tested them out in the field. That's extremely time-consuming. It's extremely difficult, and those discoveries are, of course, hugely important, but it's very hard to replicate and scale up. Today, the aerospace industry uses computation to design new aircraft. We use models of physics, in this case, fluid dynamics, in order to achieve that. I think there are really 2 things that are required for an industry to base the product design on computation. And these are, firstly, a model of the world. So in the case of aerospace, we have the Navier-Stokes equations. These tell us about the fluid dynamics, and they predict accurately what potential, let's say, wing designs what that impact will have in a realistic system. And so we need these accurate models of the world. We need very high level of predictability in order to rely on these equations, on these models, to make predictions about the future. And the second component we need is the computational power to solve these equations. And there's no surprise that the aerospace industry is one of the largest consumers of HPC capability. And in the case of classical physics, in the case of the Navier-Stokes equations, we really do have that computational power. And that's what enables an industry like the aerospace industry to design products using computers. Now, that contrasts with several other industries. In particular, there are really significant industries where we still discover new products. These include really important challenges that humanity faces. So healthcare, we do drug discovery, we discover a new vaccine. In material sciences, we discover new materials. We discover improved industrial processes. And in the search for new catalysts, for example, to capture carbon, we discover these catalysts. And what these have in common are that they are all, the fundamental physics is microscopic. It's the physics of electrons and atoms moving across a surface or interacting with other microscopic electrons and atoms and molecules and so on. In healthcare, the majority of drugs target a specific protein. Protein is made up of atoms. We have decoded the human genome, but what we really want to know is how those pieces fit together. The genome is like a parts list, and we want to understand how those pieces fit together and then how they move over time. Because as a protein moves, it opens up new potential binding sites. So from healthcare to advanced materials and the search for new catalysts, the simulation of the microscopic world is incredibly hard. And here we have one of the components. We have a model of the microscopic world. It's called quantum mechanics. Dirac's equations tells us about the interaction of particles, of electrons, how they move over time, their binding affinity. But what we don't have is the computational power. Right? We don't have the computers that we need in order to solve these equations. So I'm going to elaborate a bit on this and dig into some of the detail. And I think this is really the key foundational concept around building a quantum computer, that there are fundamental base problems that we cannot currently solve. We can change the model, we can approximate quantum mechanics, and indeed computational chemists and material scientists do this all the time. We could use machine learning, we could use data to try to estimate properties of the model, but that's very limited to the space that our data set covers. It doesn't allow us to predict away from that data set. So we have a perfect model of the world, and what we don't yet have is the computational power. This model is such a good model that quantum mechanics predicts, Dirac's equation predicts the entire periodic table, properties of every element. As an undergraduate, this was what got me so excited, that this model of the world could be so predictive that it would explain something that up until that point had seemed very mysterious. So quantum mechanics predicts the lower half of the periodic table, and when you add relativistic effects, you get the rest of the periodic table. So this is such a powerful model that we call it a law of physics, and it's such a hugely successful model. Predicts the black body radiation, and it's such a fantastic achievement. In fact, even early on in the discovery of this equation, Dirac wrote this beautiful quote that I absolutely love. He says that the underlying physical laws necessary for the theory of a large part of physics and the whole of chemistry are thus completely known. We've solved all of chemistry, he's saying. And the only difficulty is that the exact application of these laws leads to equations much too complicated to be solvable. So this was really Dirac's point in 1929. Of course, then he went on to explain how we could make some approximations, and what we're coming back to here is the ability to solve these equations directly. So what makes quantum computing so hard? What makes quantum mechanics so hard? Well, it's really superposition, and just to elaborate a bit on that, if you have a single quantum bit, that can be in a superposition of two basis states of 0 or 1, and so we need two complex numbers in order to represent the state of that bit. Now, if there are 3 quantum bits, we call these qubits, we need 2 to the power 3 coefficients, complex coefficients. And in general, we need 2 to the power n coefficients for n quantum bits. And if you want to accurately model a molecular system, typically we need on the order of 10 basis elements for each electron. So we need on the order of 10 to the n coefficients for each electron, or 10 qubits. And so Moore's law in classical computing doesn't help us. In the 1980s, we could simulate approximately 2 electrons. By the mid-90s, we could do 3 electrons. We're up to maybe 4 to 5 electrons right now, but this really doesn't scale. I mean, we want to simulate thousands of electrons, right? Much more complex systems. So Feynman, 40 years ago, proposed a really interesting idea. He said that nature is not classical, it's quantum mechanical, and we know that classical mechanics does a very poor job of simulating quantum mechanics. In fact, there are results like Bell's inequality which show that you can't simulate all of the effects of quantum mechanics with a purely classical system. And so this idea that if you're going to simulate a quantum system, you'd better make the machine that does the simulation quantum mechanical. You need some kind of controllable quantum system. And that's what we now call a quantum computer. And indeed, quantum computers then will transform these industries that currently use discovery into industries that use design. Because for the first time, we will have both an accurate model of the world and the computational power in order to solve that. So for me, this is the big picture reason why. Like, why do we need a quantum computer? Why does the world need quantum computers? It's because of this reason that there are important foundational industries like drug discovery, like materials design, that cannot design products using computers because the fundamentals of these industries are quantum mechanical. And if we can build a quantum computer, then we could transform those industries. We could radically accelerate our ability to design new medicines or new materials and so on. So this is the huge goal. This is why I'm dedicated my career in the last 20 years to quantum computing. And so really now the challenge is how to do that. And so what I'm going to talk about in the rest of this talk is how do we make quantum computing useful sooner, right? How do we get to this amazing potential as soon as possible? Because the world really needs quantum computers. So I'm going to start by talking about the progress that we have made so far. The last 2 decades has seen enormous progress in our ability to build the components that make up a quantum computer. And indeed, the trends are remarkable. We have seen an effective Moore's law in quantum computing. So what I'm plotting here are experimental results from 2 of the leading approaches to building a quantum computer. So the first is ion trap systems, and the second is superconducting systems. And what I'm plotting is over the years, how good are these experimental labs, or these physics labs, at building one of the key components, which is a 2-qubit operation. So an operation that acts on 2 quantum bits and entangles them. That's really the one of the hardest elements to build, and so that's why it's one of the key metrics. So each of the data points here represents results published in one of the leading journals, such as Nature, Physical Review, and so on. And what we're seeing here is a trend, right? Because this is a log plot, and we're seeing a straight line. So we're seeing a doubling in our ability to build the basic components. The quality of that components is doubling every 1 to 2 years. Now, the slope of these curves, I think, is not the issue here. This plot is not meant to compare these two technologies. The point I'm making is simply that there is a trend that has continued for 15 to 20 years across two different types of qubit, and we have this remarkable, totally amazing ability of the groups working in physics laboratories to control individual quantum systems, or to create individual quantum systems, to isolate those from the environment, and to for example, suppress higher level energy levels and so on. Like, this is really absolutely amazing progress. But to get to useful quantum computing, there's a big gap between where we are today and where we need to be. And that's what I want to talk about. So that gap won't be closed purely by allowing this trend to continue, because we need to perform calculations that are accurate up to 1 in a billion. So this is saying that we can do 1 in 1,000 approximately operations before failure. And we need to do 1 in a billion operations before failure. And so closing that gap is really key. To unlock the huge potential of quantum computing, what we need are huge increases in scale. So we need to take these components and build much larger systems. And we need large reductions in the system errors. In order to do that, we need systems engineering. We need to use techniques like error correction in order to bridge the gap between the size of the computation we need and the component level error rates. So this looks a lot more like an SSD driver. There are noisy components, and error correction is used in order to suppress those errors at a larger scale. So what we need is systems engineering, and I'm going to talk through how we are doing that at Riverlane. So the first thing I want to cover is the model of computation, because systems engineering teaches you to reduce the problem into small chunks as far as possible, to really focus on those unit tests of the individual components, because by the time we've built a large-scale system, that really needs to work, because at that point we won't be able to detect or find the problems in the system. Like, it's too complex, and so we need extensive unit testing. We need every component to work, and so the first thing I want to talk about is the model of computation, because I think this is really important, and is something that was very influential in the development of classical computing. So in classical computing, the von Neumann model was very changed how people programmed or thought about computation in the 1950s. And here in Cambridge, the first machine was built that followed that von Neumann model, that separated the memory from the program. And so, the EDSAC machine, that was a huge success. In fact, it was mentioned in 3 Nobel Prize winning speeches. And I think there's a lovely analogy there with quantum computing, that I believe the first large-scale quantum computer will be used to make significant discoveries on the scale of Nobel Prize winners. So for me, the great goal is to build this quantum computer and have it be as successful as the EDSAC machine. And I think that getting the model of computation right is really key to doing that. So there's one model of quantum computing that was made popular by the Bible in this field. It's a fantastic book. I highly recommend you read it if you're new to quantum computing. At Riverlane, everybody who joins is given a copy of this book because it's so foundational. It was written in 2000, and it proposed that the model of quantum computing look a lot like the circuits that we draw in classical computing. So established the quantum circuit model, quantum computing. So there are wires. These are representing qubits, and there are gates that are performed on those qubits, right? And I think this is a really valuable model. It's helped us develop many of the techniques, such as error correction, such as quantum algorithms. Many of the quantum algorithms reason about computers in this language, and I think this is very important. But when you visit a quantum computer, you don't see this circuit. A quantum computer looks like this, right? It doesn't have the property that there are wires and you apply gates to them. A quantum computer operates in a different way. There are qubits inside this dilution refrigerator. So this is a superconducting system. And there are instruments that send signals into the qubits and analyze the signals as they come out. So microwaves are sent into the dilution refrigerator. And so you should think of this as having qubits, and we apply operations to them. There's a control system that sits on top. That control system is entirely classical. There's nothing quantum about the control system. It consists of, currently in these systems, FPGAs triggering analog waveguides or modulators and so on. And so this is entirely classical control electronics. And so this model, the model of quantum computing is that there's a control system that's sat on top, and qubits that are underneath. And so this is how we program a quantum computer. This is how we reason about quantum computing in the laboratory. And so at Riverlane, we are using this model of computing to develop this infrastructure, right? The ability to run programs in this model. So we call this the operating system for quantum computing, because operating systems are what make quantum or what make computers useful. So it starts at the bottom with control, where we need to manage the many digital and analog components of the qubits. So we need the ability to trigger signals within tight timing constraints, highly synchronized signals across a very increasingly complex system. Having done that, a quantum computer has thousands of system parameters that need tuning. And that needs to happen automatically because we need to bring up the quantum computer. We need to constantly keep it online. We need to constantly manage how the system is drifting, for example. And so that's a consistent process that needs to be automated. On top of calibration, then there are kernel services, more traditional kernel services. So the scheduling of tasks in the system, these sit at a higher level because they are orchestrating many of the lower level components. And then the most important task of the operating system is error correction, because quantum error correction is what unlocks the high value applications of quantum computing. So within the, so I've plotted here the projected TAM. I mean, there are various different projections. So this is Boston Consulting Group that I'm using here. As the size of the quantum computer increases, there's a NISQ era that we are currently in. So this is noisy intermediate scale quantum. And this is a fantastic space to be. It's a really exciting time now in quantum, because we have testbed systems on which we can test and demonstrate some of the core unit tests that are going to go into building a much larger system. We are understanding key problems like how errors propagate in a system, how errors are managed as the system scale increases. And there's clearly a market for NISQ devices. Companies and governments want to test and understand the technology. But that market plateaus without error correction. So error correction is what really unlocks these high-value applications, unlocks the ability to design medicines instead of discover them. So I'd like to talk a bit about what error correction is. I'm just going to give you a brief overview and then move on to why error correction is an exciting and key technical challenge. So error correction is, quantum error correction is very similar to classical error correction in that we take many copies of the system and spread out the information across that system in order to protect against a single error, right? So if I spread the information of single qubit amongst all of these qubits and one of them fails, then I can still recover the information. Now, there are some key differences. The first is that in quantum computing, you can't look at the state of the computer. So I talked about superposition as being one of the key things of quantum mechanics. And the second key thing is that it stops being quantum mechanical as soon as you look at it. So if there are two things that you take away from this talk, that quantum mechanics is actually quite simple, it has superposition, and don't look at the system, then I'm happy. So we have to do error correction somehow without looking at the system, without copying the information. And in fact, error correction was identified very early on in the development of quantum computing as a key problem. And the reason for that is that a qubit is often represented as a state on the ball, a point on this ball. So we have the 0 and 1 states, but the register can be in any superposition, so it can be in any point on this ball. Now that looks suspiciously like analog computing, and analog computing we know doesn't scale because of experimental errors, because of errors in the system. And so early in the development of quantum computing, many of the pioneers recognized this and developed a theory of error correction that could be used in quantum computing. This culminated in the Threshold Theorem. And the Threshold Theorem says that once the component error rates are sufficiently low, once every component in this system is below some threshold error rate, then there is a theory of error correction that means we can perform arbitrarily long calculations, and that cost of doing that is relatively low. It's logarithmic in the system size. And that's a really key result, because it says that we don't need to continually hammer in on the component physical error rates. Like, we have to get them below a threshold, sure, but we don't have to get them to 10 to the minus 15, because we can use error correction to achieve that. We can use error correction to bridge the gap between the component error rates and the error rates we need to perform useful computation. And so this is a wonderful theory of how to use, for example, classical linear codes, how to apply them in quantum systems. There's much we could dive into here. But I think the key takeaway is that it's well understood in theory, but has not been implemented at scale. So this year has been a fantastic year for quantum error correction, because we've been able to demonstrate some of the unit tests. So the ability to read out the syndrome of the code, the ability to run on a small system and error correcting code that shows that you can reduce the system errors compared to the component errors. So these are really fantastic results just this year. And so what needs to happen now is to implement error correction at scale. And there are several challenges to doing that. I'm just going to talk about three. So the first is that error correction has to happen very quickly. The classical control system that's sat above the qubits has to be responding to the information that's coming out at the speed of the qubits. Right, so error correction has to keep up with the computation, the quantum computation. If it doesn't, the whole thing grinds to a halt. So in a superconducting system, that needs to happen at a rate of megahertz. So 2 to 3 million operations per second. So between every computation on the quantum computer, between every quantum gate, we need to perform error correction. And so error correction is a key bottleneck in the production of a large-scale system. Secondly, error correction requires information from the entire system, and it needs to update the entire system. So we need large-scale coordination of millions and ultimately trillions of components. So we need a large-scale coordination of this heterogeneous system because there are waveguides, there are analog and there are digital units. Some of these are operating at different clock rates. So we need large-scale coordination of that system. And finally, although the long-term future of error correction is that it is small in comparison to the complete computation, the route to error correction has a very steep hill that we need on the order of 1,000 physical qubits for every logical qubit if our architecture is constrained to a two-dimensional lattice, which in many systems is an engineering constraint. And so we need to do better than that. We need to reduce the overhead of error correction in order to produce a useful quantum computer sooner. And that's really the goal. That's really that's the mission of Riverlane is getting to quantum computing sooner. These are some of the problems that we are working on, that we are excited about, and are obviously always happy to talk more about this. So to summarize then, computation is central to the design of many new products, but there are industries where we still discover things and we can't yet design them. And quantum computing brings that ability to really foundational and fundamental industries. In order to do that, we need systems engineering, because quantum computing is a technology that humanity needs, and we need it as soon as possible. And so the shift from demonstrations in laboratories to large-scale quantum computers will be enabled by systems engineering, by solving some of the key challenges, such as how to build a large-scale control system, how to use error correction in order to remove system errors from that. So I'm just going to finish now and say thank you very much. I hope you've enjoyed this talk. Please do get in touch if you have any questions. Always happy to answer and to talk more about what we're doing at Riverlane.